Welcome to this guide on running the cutting-edge Voxtral 4B text-to-speech model directly on your Apple Silicon Mac. We're using the MLX framework, which is Apple's own high-performance machine learning library. Specifically, we'll be working with the 4-bit quantized version of the model. As you can see in the table, this version is incredibly efficient, using only about 2.5 gigabytes of RAM and running faster than real-time, making it perfect for 16 gigabytes M4 Max. In the next section, we'll cover exactly what you need to get started. Before we write any code, let's ensure your environment is ready. First, you need a Mac with an M1, M2, M3, or M4 chip. This setup will not work on Intel Macs. You'll also need macOS Ventura or later, and Python 3.10 or higher. The model itself is about 2.5 gigabytes, so make sure you have that space available. Crucially, because this is a Mistral model, you must accept the license on Hugging Face and generate an access token. We'll use that token in the next code cell to authenticate and verify that MLX is correctly installed on your system. In this first code cell, we're setting up our authentication and environment checks. First, we load the Hugging Face API key from your environment variables using the .env library. We then log into Hugging Face using that token, which allows us to download the model later. We verify the login by printing your username. Immediately after, we perform a critical check. We try to import the MLX core library. If successful, it confirms we are running on Apple Silicon and that the Metal GPU is available for acceleration. If you see the green check marks and Metal GPU true in the output, your system is perfectly configured to proceed. Now that our environment is verified, let's talk about loading the model. The beauty of the MLX ecosystem is its smart caching. The first time we run the code in the next cell, it will automatically download the 2.5 gigabyte model file from Hugging Face to your local cache. However, on every subsequent run, it will load instantly from your hard drive without needing an internet connection. This makes iterating on your audio projects incredibly fast after the initial download. Here we ensure the necessary Python packages are installed. We first print the path to the Python kernel we are using to be transparent about our environment. Then we use a shell command to install mlx-audio with the specific TTS extra, along with soundfile for saving audio and tick token for tokenization. The script then verifies that these packages are actually visible to the kernel by checking the import specification. If you see green check marks next to mlx_audio, soundfile, and tick token, the installation was successful and we are ready to load the model. This is the moment we load the actual AI model. We import the load function from the mlx_audio toolkit and define our model ID as the 4-bit quantized version. When we call the load function, the system checks the cache. If it's your first run, it downloads the approximately 2.5 gigabytes file, otherwise it loads it instantly. The output shows the model loading the Tokenizer, which is the specific tokenization method this model uses. Once you see model loaded successfully, the heavy lifting is done, and the model is resident in your Mac's memory, ready to generate speech. Before we generate audio, let's look at the variety available to us. Voxtral 4B comes with 20 preset voices covering 9 different languages. Whether you need a casual male or female voice in English, or you want to switch to French, Spanish, German, Italian, Portuguese, Dutch, Arabic, or Hindi, the model supports it natively. You don't need to train anything. You just select a voice ID from this list. In the next cell, we'll put this to the test by generating our first piece of audio. Now we move to the generation phase. The model works in a streaming fashion, meaning it produces audio in small chunks as it generates the text. Our code will collect these chunks in memory and then stitch them together into a single WAV file at a high sample rate of 24 kHz. This ensures we get studio quality audio. Let's write the code to define our text, choose a voice, and start the generation process. Here we execute the generation. We define our input text, select the casual_male voice, and set the output file path. We create a helper function to calculate the duration of the audio as it streams in. The core logic is a loop over model.generate. As the model processes the text, it yields audio chunks one by one. We convert each chunk to a NumPy array and append it to our list, printing the progress in real time. Once the loop finishes, we concatenate all the chunks into one large array and use the soundfile library to write the final WAV file. The output confirms the total duration and sample count, telling us our audio is ready. We've generated the file, but let's hear it. In the next step, we'll use a standard Jupyter library to play the audio file directly inside the notebook interface. This allows you to instantly verify the quality and tone of the generated speech without leaving your browser. This is a simple but powerful cell. We import the audio display class from IPython and call it with the path to the WAV file we just created. When you run this, an audio player widget appears right here in the notebook. You can click play to listen to the casual_mail, voice reading our test sentence. This confirms that the entire pipeline, from model loading to file saving, is working perfectly.
In today's MysteryBytes-Labs session, we are learning to generate studio-quality audio using Voxtral TTS on our local machine with zero subscription cost. Share your favorite voice in comments.
Now that we know it works, let's explore the versatility of the model. In the next section, we'll generate the exact same sentence using 5 different English voices. This is a great way to compare the nuances between the casual, cheerful, and neutral styles to see which one fits your project best. We are now running a comparison loop. We define a list of 5 different English voice IDs. The code iterates through each voice, generates the audio for the same test sentence, saves it to a unique file, and immediately displays the audio player. This creates a side-by-side comparison in your notebook. You'll see the output print the voice name and render a player for each one, allowing you to quickly audition the casual_male, casual_female, cheerful_female, and others to hear the distinct personality of each preset.
Quick brown fox jumps over the lazy dog near the riverbank.
Quick brown fox jumps over the lazy dog near the riverbank.
The quick brown fox jumps over the lazy dog near the riverbank.
Quick brown fox jumps over the lazy dog near the riverbank.
Quick brown fox jumps over the lazy dog near the riverbank.
One of the most impressive features of Voxtral is its native multilingual support. It doesn't require separate models for different languages. It handles them all in a single model. In the final code cell, we'll demonstrate this by generating a sentence in French, proving that we can switch languages with zero overhead and just by changing the voice ID. Here is our multilingual demonstration. We define a tuple containing the language code, the specific French voice ID, and a French sentence. The code structure is identical to our previous loops. We generate the audio chunks, concatenate them, save the file, and display the player. When you run this, you'll hear the model speak fluent French using the fr_male voice. This confirms that Voxtral is a truly global model, capable of handling multiple languages seamlessly on your local Apple Silicon hardware.
Bonjour, je suis un assistant vocal multilingue.